Hello, Year 7. Today's lesson is going to be a bit different because we're going to do a little bit on mass versus weight. And then we're going to do like a bit of revision of everything that we've done so far about forces. So to start with, which would you rather have, fall on your head, a ton of bricks or a ton of feathers? I just want you to have a think about that. Then, don't really look at the lesson objectives today because we're changing it a little bit. So I'm just going to read this. Years ago, an Italian scientist, Galileo, thought that objects would fall at the same speed when dropped at the same height. He tested this method by dropping 2 cannonballs from the Leaning Tower of Pisa. The cannonballs were made of the same material, but one weighed 10 pounds and the other weight was 1 pound. The Greek philosopher Aristotle thought that heavier objects fall faster than lighter objects. So, who was right? And how would you be able to test that? Have a little think. How would you be able to test it? What would the problems be? Because back then, these people had to sort of think about these problems without computers and just their brain and not really anyone else to talk about because they were thinking about something that was so completely new. Hopefully, we know the non-contact forces because we have done them in a previous lesson, but absolutely we need to know about gravity. I'm going to skip past the electrostatic force. I'm going to keep going. Now this is the important bit. Mass versus weight. Here, this is your equation that you need to know, right? Weight equals mass times gravity. Okay? Mass and weight are not the same thing. Mass is measured in kilograms, and your mass is the same everywhere, assuming you don't chop an arm off, okay? Because the mass is the amount of stuff or the amount of matter that you have inside of you. So if I got a 1 kilogram block of metal and I took it to the opposite side of the universe, the mass would still be 1 kilograms. But the weight is a force. Weight is measured in newtons, okay? It is a force that is dependent on your location. And it is related by this equation. Weight, which is W, equals the mass times the strength of gravity. Now you need to write that down, please. You've got it on here. Now, what this is saying is depending on where you are, depends on your weight. On Earth, the force of gravity is not 10 but 9.8, but we were going to round it to 10 for this example here. Let's say this dinosaur, I should say, has a mass of 1,000 kilograms. Okay. The force of gravity on Earth is 10 newtons per kilogram. So what is this dinosaur's weight? Well, we know that the weight here equals the mass times the force of gravity. Okay? Or the acceleration due to gravity. So, well, what's the weight? We don't know. But what's the mass of this person? Well, this dinosaur, sorry. It's 1,000 kilograms times by, well, the force or the strength of gravity on Earth is about 10. So the weight of this dinosaur is 10,000 newtons. Okay? So let's just say a person has a mass of, say, 60 kilograms. What is their weight? Because I know you get on the scales and you see, oh, I weigh 12 stone or I weigh 35 kilograms or whatever. That's like you're talking about your mass there. But we do use them interchangeably in general discussions, but in science we've got to be very careful about making sure when we say mass we're talking about something in kilograms, and when we say weight we're talking about something in newtons, which is a force. Well, if their mass is 60 kilograms, what is their weight? Well, their weight would equal their mass, so 60 kilograms times by the strength of gravity on Earth, so their weight would be 600 newtons. Okay? Now, very quickly, I just want you to calculate the weight of the dinosaur on these different planets. Now, remember, the dinosaur has a mass of 1,000 kilograms on every single planet. So what is the weight of the dinosaur on the Moon, Saturn, Mars, Venus, Jupiter, and Neptune? So just pause it now, have a quick calculate. If you do not have a calculator, you can press the Windows button, type calculator in, and it should pop up. So pause it, have a little go, and then unpause it when you're ready. So hopefully these were quite straightforward. Now all you had to do was get 1,000 kilograms and times it by the gravity on each planet. So 1,000 times 1.6. The dinosaur has a weight of 1,600 newtons on the Moon. Okay, yeah, so it's quite straightforward. Hopefully you got them right. Now we are going to skip this bit, and I want you to watch this video. So this is a really good video, and I'll put the YouTube video in the timestamp of the one that I've uploaded. So you can either just click down here and watch it. I think it'll be better on YouTube because it'll be better quality. But this is a really cool video. It's got Brian Cox in it, and he talks about dropping a bowling ball versus dropping a feather, and will it hit the floor at the same time or not. I think it's cool. Now once you've done that, what I want you to do, the last thing I want you to do, is if you look at what we've learned so far, we've learned about forces, okay? We've learned about drag forces and friction. We've learned about stuff being balanced and unbalanced. And we've learned about mass and weight. I'd like you to do a very quick little revision material. It can be a poster, it can be a PowerPoint, just on everything we've done so far, just to get your brain sort of caught up with everything and get everything organized, ready for when we go back. Okay, and once you've done that, that is today's lesson finished.